Okay, let's start. Any questions? Anything you want to say before we start? Okay, so today you'll learn binomial theorem. We'll also discuss something called Pascal's triangle. Okay, let me start with reminding you what we learned last time. First, we learned that if you try to choose some people out of a big, large group of people to form a picture taking in an ordered way, then you can do this. You can count the number of ways you can do this by using a product rule. So given n distinct objects, we can choose R of these objects in an ordered way. So to put in a list to order them linearly in n times n minus 1. So we have to multiply this R many times. And to multiply this R times, you have to go to n minus R plus 1. In this many ways. And we call this permutations of n choose R, P and R. There's a similar thing called combinations, but this time we ignore the ordering. Okay, so in the 2, this is combinations. Given n distinct objects. So this is like n students, say 10 students, and you're forming a committee with 3 members. It's this combinations is that. We can choose R of these objects by ignoring the order of the choice. In how many ways? So this permutations comes in because you first choose them as if you're choosing them in an ordered way, but then you divide by the number of ways to order R people to adjust this calculation. Okay, so it was basically PNR divided by this number, which we use the notation R factorial for that number. And this is called combinations. So this is the definition of combinations. Combinations of n choose R. And if you look at it a little bit more careful, you can also write it n factorial divided by n minus R factorial times R factorial. So it's a more involved formula. In fact, we can introduce notation for positive integers R and n with say R is less than n, we use n choose R is going to be this thing. And there are a couple of special cases, like n is 0 and so on. So like from this formula, n choose 0 and n choose n are 1, but you can also define 0 choose 0 and so on. And n choose R is 0, for r bigger than n. So for other cases, we just take it null. It's 0. So this notation, n choose r, is subject to many of the nice questions or many of the combinatorics. So for example, you could try to use these combination formulas for multiplying things. So it's not only useful for solving word problems, but you can also use them for basic arithmetic. So binomial theorem helps us with this basic arithmetic. So binomial theorem, it says that for any, for n bigger or equal to 0, for any variables, basically. So x and y doesn't have to be real any numbers. You can write a formula for this now using a binomial, these coefficients. So this sum has this term, and then the last term is n choose n. So for example, x plus y square is 2 choose 0 x squared, 2 choose 1 x times y, 2 choose 2 y squared, which becomes, because 2 choose 0 is just 1 x squared, 2 choose 1 is 2 by this formula again, 2xy plus y squared. So you can sort of expand these numbers using this formula. Now I'd like to go into this a little bit, sort of explain why this is true, and maybe one of the ways to approach to this is actually start with this observation. So this is a very valuable observation, which will be used for this theorem, which we'll use. So for every n and I, the following identity holds. So if you choose I from n plus 1, it's same as choosing n from I. This is something that anybody who is using this n choose r should know. It's basically saying that if you have n here and I minus 1 and I on the bottom, if you add these two numbers, you get the n plus 1 version of the same thing. We can check it. For example, like say 5 choose 3 and 5 choose 4. You can write it in 5 choose 3 is this, 5 choose 4 is this. So you can cancel out certain things. You get 10 plus 5, 15. And then this says that it's same as 6 choose 4. And you get 15. So when you write it in terms of all these factorials, it looks almost like a miracle. I mean, all this cancels and so on. and gives you same formula. But we'll see later that there's a very, very simple reason why this is true. But for the time being, suppose this is true, and let's assume this. Can you find an inductive proof that then this will be true? That's my question. This will be a good exercise for induction. So I want you to think about, assuming that this is true, can we find an inductive proof for this one? And how should I set my induction? This is something that for all integers, right? Positive integers. So that means this is exactly the situation for induction. So it actually, if you ignore the 0, we can actually start with 1. 0 is obviously true, so maybe we can even say it starts with 1. So how should I set an induction proof for this?
We can use usual induction proof.
Let me go to here. So let's call this a proof of binomial theorem. By induction. We'll be doing it by induction. So because n equals 0 is obvious, I mean x plus y to the power 0 is just 1. Any power of 0 is 1. And 0 choose 0 is declared to be that. So actually, everything looks funny and n equals 0. So we can actually say that let's start with 1. For 0, it's almost not reasonable statement. Let's start with 1. So check for n equals 1. So for n equals 1, we're looking at this. If this is true. And 1 choose 0 is 1, 1 choose 1 is 1. So this is true. They're both 1. And one power, first power of anything is itself. So we don't need to. So now I assume it's true for n. Now we want to show it for n plus 1. So n, now I can assume this is true for n. Now I want to prove the next one. What should I do to prove it for the next one? For this kind of proofs, we always start with n plus 1, try to get a formula for it, right? So for n plus 1, I have this. And the clever thing to do will be to write it like this. Because then n power, I can use the binomial theorem. So because this is now only n power, by the assumption for n, I can put the formula for that using induction assumption. Okay, so I have x plus y times a vehicle sum, which I can do one by one multiplication. Right. So if you multiply with x, you get xn plus 1. And you get n typical element, which I will say n choose I here. Let's use the I minus 1. So here you had a typical element which looks like this, I minus y, x, y minus 1. Let's say n minus. So a typical element looks like this. So now this became like this. This is when I multiply everything with x. I can do the same with multiplying everything with y. Instead of writing just under it, I write it by a little bit shift. So now I multiply everything with y. Okay? But you can see that it will become n choose 0, x to the ny. Right? So it's exactly the same thing as this one. So that's why I write it under it. And then I get n choose 1, xn minus 1 y squared. Again, this is exactly the same. So to get this, I have to have by I minus 1. So that means the coefficient should be this. Because this is coming from I minus 1. Now here we will get n minus 1, x, y, n. But the last one will be n choose n. Or 1, basically. Y to the n plus 1. So shift it, but we have exactly the same terms. This thing, and this thing, and this thing, and this thing. So that's a good thing, because now I can sum the coefficients. Right. So if I sum the coefficients, I get this. So we get this. N choose 0, x to the n plus 1. And here, n choose 0 plus n choose 1 plus n choose 0, x to the n, y, n choose 2 plus n choose 1, x to the n minus 1 y square. So like this, n choose I plus n choose I minus 1 for the coefficient of xn plus 1 minus I, yi, and so on. So just before the last one, n choose n choose n minus 1, x to the xy to the n, plus n choose n, y to the n plus 1. So the question is this what we wanted? So we wanted something like what we wanted should have n plus 1 choose 0 here. And then what we want should have n plus 1 choose 1 here. Right? And what we want should have n plus 1 choose I here. So is these true? Are these true? This is true. You can see, or look at the general one. This is true exactly because of this observation. We said that n choose I plus n choose I minus 1 is n plus 1 choose I. So this is exactly what we have. And for the same reason, this will be n plus 1 choose 1. This looks a little funny, but this is true because they're both 1. They're choose 0. Choose 0 is always 1 by the formula. And this last one is little, you have to always check the last one first. This looks like this because of, again, the formula. But this one, we need it to be this. And again, they're both equal to 1. That's why they're equal. Okay, we don't need to use the formula for those ones. So they're all true. All these are true, hold, because of observation. The observation. So we proved by induction that binomial theorem holds. It's a good practice for induction. I think it's a nice practice. What remains is to show why the observation holds. So I need to verify why this is true. But before that, do you have any questions? Anything about what we did?
In the exam, do we have to,
Huh?
in the exam, do we have to prove such observations?
This one is actually quite non-trivial fact, so we will have to prove it. I mean, if you think something is very obvious, you should be able to write it in 1 or 2 lines. If something is very obvious, and then why not write it, right? And if it's not so obvious, takes half page, then you need to write it too because it's not obvious. So this observation, you probably need to verify it. Is there an easy way to see why this is true? Any idea? Like from these formulas, can you see why you get 6? Let me show you. So why the observation is true. So you can actually easily verify this by arithmetic. By arithmetic, what I mean is that you'll be just writing the original formula for this with factorials, and then get the other one using multiplication and division. It's a very actually easy exercise. So this is by the formula, looks like this. Like this. So we have summation of 2 things, which one of them is n factorial over this, the other one is n factorial over this. So we should be able to sum these if you can make the bottoms look like similar. So first note that n factorial, we can take it out, and then we can take out a couple of more things. For example, I minus 1 lives inside here. This is actually I minus 1 factorial times I. So you can actually take that I minus 1 to the front. And this one is 1 more than this one, right? So this thing is actually 1 more than this one. So because of that, you can take n minus I factorial as well. What will remain is just this one on the first and just this one on the second one. It looks a little bit like we're trick. We have ugly thing here, but if you do this arithmetic on the middle, you get something very, very nice. That arithmetic will give you I plus this thing, which means n plus 1, times these lower parts. But I got n plus 1 on top. This is the crucial thing, because I wanted n plus 1 factorial, and I got that. So on top now I have n plus 1 factorial, and I have to just look at the bottom a little bit more. Now this is I times this I minus 1 factorial, which makes it I factorial. And this one n minus I plus 1 times n minus I factorial. So you just get n minus I plus 1 factorial. But that is n plus 1 minus I factorial, right? So you actually got n plus 1, choose I. So we actually made it by just direct calculation. Uh-huh.
And then also observe it by looking at summation.
Huh?
Because it says choose 4 plus
Uh-huh.
people, and if you call one of the persons X,
Yes, exactly.
if we include him, you can choose 3 from 5. If we don't include him,
Mhm.
you can choose 4 from 5.
So this is sometimes called combinatorial proof or combinatorial argument. If your formula is the number of something, number of ways to choose something, number of ways to do something, then it is actually sometimes possible to show that two things are equal by showing that there is one thing that you can count two different ways, where one way will give this, the other way gives this. This is called verifying something using a combinatorial argument. So what the suggestion is, we already know this is the number of ways to choose I minus 1 people out of n people, say students or something, say students. And say one of the students is, what's your name? Batuan. So one of the students is Batuan. We're choosing a committee with I students out of n plus 1 students, and one of them is Batuan. So when you look at this, by addition rule, we can actually think this as sum of two different situations, where in one situation, Batuan is in the committee. In the second situation, Batuan is not in the committee. So this is number of ways to choose. Choose a committee with Batuan in it. And this is number of ways to choose without Batuan. So one of them is with Batuan in it, the other one is without Batuan. And Batuan cannot be in the committee and not in the committee at the same time. He is either in the committee or not in the committee. So this is exactly the situation where you had the sum rule, that you have exactly distinct cases with no intersection. And each of these can be counted easily, because if Batuan is in the committee, you already know one member that is there in the committee. So you are choosing a committee with I minus 1 students, and you have n students available because Batuan is no longer available. So you'll be choosing I minus 1 students out of n students for the first case. And Batuan obviously is in it. For the second, we know Batuan is not in it, so we have n people to choose from. But now I know Batuan is not in it, so I have to choose exact I students. Because Batuan is not in it, so I have to choose I students. So this sum has to be equal to that. So that's another way to verify this. Thank you.
A way to verify this or just interpretation?
No. This is actually as good proof as the other one. Actually better proof than the other one. I actually, in the exams, ask you, prove this using a combinatorial argument. This is a typical question that's a very solid proof. Because what you're doing is that you're saying, I am going to count this set. First this way, second this way. And because the set cannot have two different number of elements in it, these two has to be equal. Okay? Basically, the idea is that you want two formulas to be equal. You just find a set who one way of counting gives one formula, the other way of counting gives the other formula. This can get very, very difficult and hairy. If you are okay with what we did, I can give you another example of this situation. But I want to make sure you're okay with this. Is that good? Mm-hmm.
This was that you are using, you are fitting a model formulation.
Yeah, I choose a set. I say count this number of, and you say this is equal to this, but it's also equal to this.
I understand, but
No, it's a very valid proof. I mean, it's a set you're counting two different ways. It's actually very common. Let me give you another example. But to give you another example, I'm actually going to tell you a couple of things first about Pascal string. So, in 5 minutes, I'll give you another example of this. And the example will come from this Pascal's triangle. Now, many of you probably know this. Actually, in this course, we'll learn another version of this with stirring numbers. But this is the one that with combinations. And it says that if you start with 1, with 1, 1, and in each step, put 1s at the end, but the numbers in the middle obtained by summing the numbers on top. So 1, 1s at the ends, but always sum these numbers to form a new row. This process will give you all these numbers in a row where you can interpret them. Say this is the 5th row. You can interpret these numbers as 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, and so on. So this will be 5 choose 0, 1, 2, 3. So this is 5 choose 3 because you're going 0, 1, 2, 3. Okay? So this number, 0, 1, 2, 3. 0, 1, 2, 3. So 6 choose 3. So it's a very simple process that each time you get a new row, the numbers in that row are exactly the 6 choose 0, 1, 2, 3, and so on. So you can easily form this. That means for pretty much everything, you can use this to calculate the choice and choose R's for small n. That's what this is. Can you tell me why this works? Why does it give you n choose R? Is this a miracle, or is there a reason why this gives you the n choose R's?
First of all,
Yeah, it's exactly actually saying the same thing as that observation. See, this is 6 choose 3, this is 5 choose 2. So this, which says that obtain a new row by summing these numbers, which means you're summing 5 choose 2 with 5 choose 3 to get 6 choose 3. This is just a convenient way of saying that repeated usage of this observation will give you all these n choose R's. That's all it says. There's nothing But it's a very nice way of getting these numbers. So each time like you're struggling with 7, choose 3, you can actually form these triangles and get those numbers. There are couple of things I want to say about this. First, when you sum the numbers on each row, you get another miracle going on. You get the 2 power n's. So you get 2 power exactly the row. So that's one thing, that anytime you sum these things, you get 2 to the number. There's a couple of other things you can obtain from this triangle, but let me write these. Another thing you get is that if you sum these numbers, you get this number. 1, 3, 6, 10, you get 20. So anytime you form a sort of row like this, in sum these numbers, you get this number. Another strange thing is that if you sum the squares of the row, what you get. Let's try what you get. So instead of the normal sum the squares. So what you get in 6, 9, 9, 18, 20, 36, 16, 16, 32, 68, 70. 100, 200, 250, 252. So what are these numbers? Can you tell me any guess what these numbers are? What's it? 2 and choose n. So you're saying that these numbers are exactly these numbers. So 2, 6, 20. So we're seeing that the next one here is 70, which is true. So those are the numbers. So it's 2 and choose n. Now my question, this is find a combinatorial argument. Proving the equality. This was a final exam question last year, or 3 years ago or something. So you can see that you can play with a diagram, find a miracle equation, something like this one, and say, why is it true? Now, if you try to prove this using the arithmetic, this is actually not that easy to prove by arithmetic because it's squares of those factorials. So if you try to prove it, it doesn't work. Induction also doesn't work in this case. It's very ugly. So what you're left is actually a very clever combinatorial argument, which says this equals to this. Can you find that argument? I don't know if you have enough time, but we have 10 minutes.
We can factor the square as n choose 0 square is n choose 0 times n choose n.
Okay, so there is another observation which I didn't say, but it should be clear. if you're choosing I people out of n, it is same as choosing who is not going to be chosen. So instead of choosing I people, you can choose n minus I people, and that will give you the I people. So this is the easiest case of a combinatorial argument, that these two are equal. You can also verify this by permutations, that's factorial formula, but these two are equal. So what the suggestion is that because they're equal, use this. Okay. So what you gain out of this? What does that mean? N choose k times n choose n minus k.
Some of the bottom numbers are always n. So it's,
So you're saying this will be, so in a typical one, you have n choose k, n choose n minus k. So the bottom parts are k. So totally you're choosing k people.
so we are always choosing n out of 2.
Sorry, the sum is n. So we're choosing n people out of 2n. But why we have this sum and giving you the same thing?
Because we have two different sets. Both has n elements.
Uh-huh.
We are choosing all of the possibilities.
So you can take this as you're choosing n students. Okay? So number of ways to choose n students out of n males and n females. Like boys and girls, basically, I should say that. N girls and boys. And boys and n girls. So we have n boys and n girls. You're choosing n people. We don't care about how many girls and boys in that. You're choosing n committee of n people. Out of these 2n total people. This can be done this many ways. 2n choose n. But in each of these, this is number of committees you can choose with exactly k boys. Right? So this is number of committees with of n people and students with exactly k boys. But if you choose k boys, you're choosing n minus k girls into the committee. But now you're choosing them from its own groups. So you're choosing k boys out of n boys. And then you're choosing n minus k girls out of n girls. So because of the product rule, you have a product of these choices. And this is only for k. But your committee can have 0 boys, 1 boys, 2 boys, k boys, or n boys. So you have to sum all of these to get all possible committees. Because a committee can randomly choosing, may have 0 boys, 1 boys, 2 boys, and so on. So because of that, you have to sum these up to get this. And this proves why they're equal. And this is pretty much the only way to prove this. I mean, this is a nice exercise on this. The other one is this one. Can you see what this means? Sum of these is equal to this. So actually it's like 2 choose 0, 3 choose 1, 4 choose 2, 5 choose 3 is equal to 6 choose 3. Something like, you can generalize this easily this is actually same as 5 choose 2, 4 choose 2, 3 choose 2, so 2 choose 2. So it's actually this formula, R choose R plus 1 choose R goes to the n, gives you n plus 1 choose R plus 1. So it's actually very abstract formula you can write also first. And you can try to prove it also with combinatorial argument. There's a combinatorial argument pretty much for all these kind of things. And you can also play with it by yourself and find other formulas here. People actually almost worship this number relations, and they found a lot of these kind of interesting things about Pascal triangles and so on. But this one also is in my exercises. I often give this as an exercise to practice. So you can try to prove this by yourself. Okay. Huh? Which one? Yeah, this is R plus 1. I wrote it R plus 1 and then changed it. Yeah, you're right. This is 2, so you get to 3. This is actually also very easy to, I mean, you can set up a combinatorial argument for this also. Very nice. But there is also other unknown. For example, if you sum these rows with plus minus, you always get 0. You can try to find what you get with the cubes of these numbers, for example. And maybe you'll find a good formula and things like that. Okay, enough all today. Friday we have a quiz.